Today's lecture is about pre-treatment of biomass, and also I think we have time to cover the ethanol production or sugar conversion into ethanol. And these are topics that have been described quite in detail or in the course book, and also that's one reason that I will not maybe go through all in such a detail, because you can of course read the chapter number 7 in the course book. So that was one of the ideas, to have a course book, and there's also material. The same as always, so if you have any questions, so feel free to ask anytime. So I will start with the pre-treatment methods, and this graph was shown already, I think, last week, and just to illustrate the biomass or biofuel life cycle that is in this graph. So we are now here in the phase 2 in this graph, so that is biofuel production, and more specifically biomass pre-treatment. And regardless of what we are making, so if there is a production or manufacturing process that is converting something, that applies at least to chemical industry. So there is the actual conversion step, but before that there is so-called upstream processing, and in this case, in this graph, it means this biomass pre-treatment. And that is very common that, let's say, the reactants are not as such suitable for that chemical conversion, which would be, for example, a fermentation of sugar into ethanol, but there are some purification step or some conversion or pre-treatment steps that are needed so that the actual chemical conversion would work best or would give the optimum yield or fastest reaction rate or highest conversion. So now we are starting with these pre-treatment steps, and there is a lot of information in the literature about biomass pre-treatment, and also depending on the area. But a lot of this knowledge of pre-treatment comes from the pulp and paper industry. They have 100 years or even longer experience in how to convert biomass like wood into something like pulp or paper. And the pre-treatment methods can be somewhat similar in pulp and paper industry and also in the making of biofuels from biomass. Not exactly the same, but there are like knowledge and expertise that stems from the pulp and paper industry. This is mentioned in the course textbook, that the pre-treatment is often one of the most expensive steps in this whole production cycle. So therefore, it's although it's mentioned sometimes that it's only pre-treatment, but the importance for the business and for the economy of that production process can be quite significant. So one should not neglect these pre-treatment steps or alternatives. Here, this is like a scheme describing these reaction pathways, some of which we have already, all of them basically covered in the introductory part last week. But if we take a look at these two routes here, so the first one is the sugar starch route, and here is pre-treatment step. I highlighted this with a blue color, so it's called hydrolysis. And if we go to the lignocellulosic side and here it's also hydrolysis, the products are the same, bioethanol in both, but because the starting material is different, so the potential pre-treatment steps and methods are also different. So although here is word hydrolysis in both and it's a pre-treatment, so it doesn't mean that they are identical. This is just a simplification of bioconversion process, how to make ethanol. There is nothing that special, I suppose. There is the biomass, pre-treatment, hydrolysis, where you get out the sugars that the yeast can ferment. Then you have fermentation step, where you convert the glucose and some other sugar molecules into ethanol and carbon dioxide. It's identical to alcohol or wine production, beer making, alcohol production, this type of steps. So once the yeast has done the fermentation and basically majority of the sugars are converted into ethanol. So if you want to use them, of course you use them as such after aging if it's like wine or some alcoholic beverages, but if you want concentrated ethanol, you need the distillation step, and this is like the distillation step is the downstream processing with respect to fermentation. So if you want to make strong alcoholic beverages, you are doing distillations. That's a very old technique, has been applied for, I don't know how long they have made strong spirits or alcohols, hundreds of years for sure. And there is basically separation of ethanol, the alcohol, from remaining water molecules. And we are interested in making fuel additives, the ethanol, so one has to remove the water. Distillation is not enough because you end up with azeotropic mixture, water ethanol mixture, and it cannot be purified to higher than roughly 91.5% ethanol concentration. If you want to remove the rest of the water, so there is azeotropic distillation with benzene, which is not usually anymore applied, and then there is the water removal using molecular sieves, these zeolite type materials. And once you get this very pure ethanol, so it can be mixed with other fuel components, and it works well, for example, in gasoline-driven vehicles. This is maybe repetition from earlier lectures to some extent. So we are now focusing on lignocellulosic biomass. We already discussed about the composition, like there is the cellulose, the hemicellulose, and lignin, which are the main components. But then, of course, you might have some fats and oils depending which type of plant or crops, and maybe protein as well. So it's a mixture, but in any case, so you can use or we prefer agriculture residue, which is kind of a side stream or waste material. Also wood residue instead of proper wood, so which would have higher value applications in other industries. Also certain waste fractions contain lignocellulosic biomass like paper waste, and some municipal solid waste can also have lignocellulosic material. So the chemical composition varies here, like we have seen already. So it depends totally on what is here in the feedstock, and that's probably quite understandable. But when we apply these pre-treatment steps, like here in this today's lecture, so it influences, of course, the different components in a different way. So here is just like if you want cellulose separated from others, so this certain woods can have 50% of cellulose, but then there is of course roughly 50% of other materials and so on. Also this hemicellulose or xylan sugars, those are easier to extract out from the wood than, for example, cellulose is rather inert, and also lignin is the third component that can be separated. But just that it's not that straightforward, that you are making ethanol and you want glucose monomers, but always you have to take into account that there are other components in the mixture, and that often those need to be separated or treated in a certain way, so that we'll get what we want, if that's ethanol or something else. But here are some things that I have taken also. Majority of this material comes from the course textbook, so you can read it from there with some additional details included. So the idea of pre-treatment is what I already told you, that to prepare the main feedstock for that chemical conversion to make that fuel. And in lignocellulosic processes, so the main aim, of course, is to remove some unwanted material, but also make the cellulose, the main ingredient, more accessible, more easier to ferment. So it's the chemical composition or the physical composition can change in the pre-treatment process. This is just to make the fermentation work better. And here one goal is to kind of remove or break the lignin, which is kind of the glue holding the hemicellulose and the cellulose strains together. And there are several methods how to do this. Ideally, the ideal pre-treatment would be very cheap. Nobody wants to pay any extra if you can get it done cheaper. Also, there are things that should be rather fast and robust. Robust meaning that it's kind of stable and can tolerate, let's say, different feed compositions, different temperatures, etc., so that it's not opposite to sensitive to something. It would be beneficial to be simple rather than very complicated. Complicated usually means expensive. If there are catalysts, so those would be beneficial if those can be recycled. And very often the pre-treatment, you'll see in the coming slides, so it's done by acid treatment. And if you are using most commonly the sulfuric acid, so it's a mineral acid, a liquid chemical, so that is often more or less impossible to separate from the sugar mixture. So therefore it's neutralized and kind of destroyed. So the catalytic function or the material cannot be used again. So it's very difficult to recycle. We are of course concerned about the environmental impact, so it should not cause harm to the nature or humans and so on. And the last is that if we aim for the fermentation, so we want a good yield of sugars that can be hydrolyzed and fermented. And there are some pictures showing that in hydrolysis, so in which steps it chemically happens. And there are also like so-called degradation products. That means that those are kind of side products or products that have reacted too far and are unwanted. So something more about that later on. Here, this list on the right-hand side has been copied from the textbook. So there are similar things that are described on the left-hand side, but perhaps in somewhat different way. So the cost factor is the same also. Well, it's not maybe mentioned on the left-hand side, but minimal waste production. So if you pre-treat some material and you produce a lot of waste, so that's of course waste that you have to handle, and it's naturally less useful material to process further. We are often talking about like wood chips and woody material. So if the pre-treatment can handle bigger particles and bigger size woody parts, biomass parts, so that's beneficial because this kind of grinding and milling is energy intensive, and you want to limit such steps in the pre-treatment. This fast was mentioned already. Of course, these non-corrosive chemicals are unwanted, and that refers usually that if you handle with corrosive chemicals, the processing equipment has to be made from expensive materials or metals that can tolerate, let's say, acids. And I think that's the effect or the aim in the pre-treatment is this left-hand picture I have showed you. It's again from the course textbook, but it shows the structure of lignocellulosic material. We had few pictures of this earlier, similar ones. So there is the lignin filaments, there are cellulose parts and also hemicellulose tightly bound to each other. And the pre-treatment breaks the structure, not totally, but it like the picture illustrates. So it opens up the structure, maybe separates some components partly from each other. But this basically, what happens is that when this pre-treated material goes to the hydrolysis, so then the hydrolysis chemicals can access easier these different components and separate those or break those further. So if the pre-treatment, if the hydrolysis would be done without pre-treatment, so the reactions would happen very slowly, and also majority of the material would probably not react at all. So that's the aim and in this pre-treatment of woody biomass. Some possibilities for making this pre-treatment. So there are like, you can group them like mechanical methods, chemical, biological, and combinations of these. So mechanical can be understood quite easily. So you are milling or grinding the material into smaller and smaller particles and creating new surface and breaking also the structure to some extent. It's time consuming and also energy intensive and thereby expensive. This is quite not that common, but irradiation. So if you irradiate the wood with, let's say, microwave, so you can heat the material and that might help to pre-treat, break the structure to some extent. But then the chemical treatment, so it's application of typically acids or bases or other solvents that help to partly break the structure and partly like react with the components already. Biological methods, you can use some microbes to break the woody biomass into its components. But I think this also might be, or this you can also combine different pre-treatment possibilities. This is just like pre-treatment process. So this picture has been, or maybe it's not the picture, it's a scheme, is from chapter 7, the course book, and shows just what things there are involved. So you have like, it's not that surprising, but maybe it illustrates that you need something in addition to the biomass that is your raw material that you want to process. So you need also sometimes, not always, but quite often, energy input, heat, mechanical energy, and also certain chemicals or additives are usually required. Once you apply these, you'll do the pre-treatment. So then you get the desired component, cellulose, hemicellulose, lignin, and or something else. Or actually, this is so general, the picture, that one cannot say that the solid would be the desired one. Here is also a liquid fraction. If you want the sugars, so you might be happy with these oligosaccharides and additives and such. So it's not clear from, but let's say that maybe easier to say that you can get a gaseous stream out from the pre-treatment with some solid residue and also with some liquid or condensable vapors. So depending what you want to do and what are the conditions, so maybe one or two of these are the desired fractions that you want to get out. Sorry, I'll try to get the box, sharing box out from the, so that I can see the text. Now I succeeded. So basically the text tells much shorter way the idea what I was trying to explain with this picture. So you get different gaseous, so liquid and solid streams out from pre-treatment, and some of them hopefully are the value added ones that you'll process further, and some that you basically separate out from the mixture. So these methods are described in the textbook. Also the table has been copied from the textbook, and for this part's discussion we have, if you remember, so for each section there is discussion and assignment, and this time's discussion is related to these particular pre-treatment methods. So the idea is that you'll take one of these and shortly summarize or describe what's it about, what's the purpose of these pre-treatment methods, and how it works. So very shortly describe. So there are, like, this list is not complete. It's something that has been described in the textbook, but if you search for woody biomass or lignocellulosic biomass and pre-treatment methods, so you can get certainly hundreds of articles, and some of them can have many more pre-treatment methods that are collected in here. So these different methods tend to have slightly different outcomes or effects, and this table is illustrating that. So if we take uncatalyzed steam explosion, so or let's take a look at these effects that are included in here. So increase surface area. So the idea is to kind of break the biomass so that there is more surface area that the chemicals can interact, or for example the acids can hydrolyze better. Decrystallize cellulose, that's one. If you are able to decrystallize the cellulose, so it's easier to break into smaller oligomers, and it's more accessible to the chemicals and other pre-treatment materials that you apply. The removal of hemicellulose, it's explained or described in the textbook that hemicellulose, because it's amorphous, it's not crystalline, so it's amorphous, so it's more reactive and hemicellulose can be removed from the wood or the lignocellulosic material quite easily. You don't need to apply much more than very hot water, and hemicellulose part will dissolve out into the liquid phase. And then you are left out with cellulose and lignin, and those you can separate. Once you hydrolyze the cellulose, it dissolves into water, and lignin remains as a solid. So it's always easy to, let's say, separate. If you have a aqueous solution of hemicellulose and the rest is solid, so simple filtration will do. The same if you dissolve cellulose, so you separate liquid aqueous solution of cellulose and solid lignin quite easily. Removes lignin. Some methods have potential to remove that. Some methods might alter. If you remember, the lignin was this non-sugar polymer matrix, so it contained aromatic organic molecules which are useful components for fuels as well, but in the earlier days the lignin has been the most difficult material to process further. Pulp and paper industry separates these three components, and often the lignin is simply burnt. I mentioned that the heat is used for the pulp and paper processes, but the lignin has this valuable aromatic building blocks or monomer units, and those are needed and can be used in the petrochemical industry to make quite important basic chemicals. So the different methods have different effects, and all of them increase the surface area. Only some decrystallize cellulose, so the ammonia fiber freeze explosion and also ammonia recycled percolation. The difference with this is that the ammonia fiber freeze utilizes like concentrated ammonia, and this lower one uses aqueous solution, which is much less concentrated. And the discussion task, or that is, you can read more about the actual methods from the textbook. So those have been explained there in a understandable way. Here, hemicellulose removal, like I said, so it's rather easy to remove. So basically all of these methods are doing, at least to some extent, hemicellulose removal. Lignin removal is more challenging and not carried out by, for example, the steam explosion, liquid hot water, and pH controlled hot water are not influencing the lignin at all. Also, diluted acid is not influencing lignin removal. But on the other hand, the lignin structure is altered in more or less all the cases here. This is more detailed information about the methods. I think there are more than most of these methods are included in this table, but this gives you an impression what type of chemicals, what type of conditions are used for the wood pre-treatment. So in majority of the cases, temperatures tend to be rather, those are not industry-wise very high, but you need to increase. We are talking about anyway temperatures often higher than 100 degrees. So it requires energy, and majority of the methods also require like increased pressure. Reaction times in some of the methods are several weeks, but on the other hand, in some methods, rather short, like few minutes. So the chemicals that are applied, so it's of course acid. So you apply sulfuric acid. There is just a small difference in concentration in this dilute acid and flow-through acid treatment. pH controlled, you use water, and this AFEX used anhydrous, so it's ammonia gas, the concentrated ammonia, and here there is 15% water solution of ammonia. This is a base catalyzed reaction, so calcium hydroxide. Okay. So the pre-treatment in a short summary. So there are methods to pre-treat lignocellulosic material, and basically that is making it more accessible to chemicals, or so that the hydrolysis can take place. And hydrolysis, this word lysis means breaking something, or well, here it's like hydro of course means water, and lysis, okay, it's separation. Probably it's the origin is separation, but I usually have understood that if some chemical bond is broken, so it can be called lysis. So it refers to this, that the long for example, cellulose, this polymeric chain is broken to shorter and shorter parts. And hydro refers water, so you'll see the chemical equation up here. So I can draw. So here is the sugar polymer, the general structure. So this refers to this is one sugar monomer, and it's the end can be like 10,000 or something. So water molecule is over here. So the water molecule basically merges with that one sugar molecule, this glucose molecule in the chain, and it breaks, and then you get, this is the sugar monomer chemical structure, but I don't know if I have a good picture. There is slightly better. But the water basically adds to the chain and breaks it so that we get these smaller sugar molecules. I think this is more or less clear. So hydrolysis, well, the idea is that you'll break the polymer into smaller pieces, and it's called hydrolysis. If you utilize water, it can be called some other lysis, like methanolysis, if you use methanol and so on. Methanol is not used in the case of this biomass, I guess, but in some other chemicals that can be broken. with that. This is the thing that I mentioned to you, that you can get degradation products. So these are unwanted products. So this is kind of a consecutive reaction where the starting material, the cellulose and water, are reacting and breaking into glucose monomers. But the thing is that when you apply these conditions, so the glucose can also react further. And then there are several alternatives, but those are not desired. So those are the unwanted products or side products. Here mentioned the degradation products. In the textbook, course textbook, there are equations and explanations what the degradation products are, if you are interested. There are also like listed different cellulose hydrolysis mechanisms. This is just this is illustrating the simplest one. So there is just that the two reactants will react and form the product, and then the formed product can react further with a, but this is more refined mechanism, that the cellulose actually, according to this, it's forming two types of species. So it's forming this shorter and shorter chain oligomers, which are here. These are the once these are broken to monomers, so you end up to desired glucose, and then the lower part is very similar to this upper simplified reaction, but it's mentioned that you might get some unreactive cellulose components, which, like it says, so those cannot be converted any further and might remain as a solid material, while this part is already water soluble. Okay, here was some of the undesired products can be these hydroxymethyl furfurals and levulinic acid and so on. But these maybe the unwanted products, well, if you want to do fermentation, these are unwanted products, but these can be utilized, and actually some of them work as a fuel components or can be converted into valuable fuels. So there is a lot of information about this in the textbook. I didn't take this because I want you to know the reaction mechanisms, but here are two possibilities. So this up here is starting material, is that cellulose, and there are two glucose molecules displayed, but the structure continues to both directions. So there and there, and one can add there few thousands of these molecules. So then we are talking about cellulose. So when you treat with acid, so this H plus refers to acid, and it can attack two different places in the structure. So it can attack this ether bridge between two monomers, or it can add this inside this molecule, this ether bridge. So the mechanisms are slightly different. Here it's proposing that because the internal six-ring structure is attacked, so the ring opens, but then it closes when the water molecule adds to it, and then you get the glucose, sugar, what you want. The left-hand side is basically similar, but the bridge breaks into two monomers, and then the water molecule adds and forms the desired end product. But the main point here was that you get a kind of refreshed view of how the glucose sugar structure looks like. So basically this hydrolysis is breaking with water, and you can catalyze it with acids and bases. Another possibility is that you utilize enzymes. So these are the biocatalysts that you'll find in living organisms and also throughout the nature. And enzymes can break lignocellulosic material into monomers, and this also is from the course textbook. So there are two possibilities that you do separately, first hydrolysis and then fermentation. But like mentioned here, so this is slightly problematic and it doesn't work that well because the formed sugar inhibits the fermentation enzyme activity. This is quite typical for these reactions, that some formed chemicals can slow down the rates or inhibit the catalytic activity. And then, so the idea in that improved approach is that you aim to keep the sugar concentration low, and that is done in the simultaneous process in a way that you'll do at the same time the hydrolysis, so production of glucose molecule, and you do the fermentation which consumes the sugar molecules. So you make ethanol and keep the sugar concentration low so that the enzyme works faster and you get the end desired product faster. These are just two different approaches to do the similar things. Enzymes can be rather complicated, and also typically enzymes don't tolerate very high temperatures, so they work. Majority of enzymes work best close to, let's say, body temperature around 40 degrees Celsius. But these cellulases, enzymes that break cellulose or catalyze the cellulose hydrolysis. So there are different ones. The names are not so important, but the different enzymes have different functionalities. So they attack different parts of the chain. Some attack at the end of the chain, some attack in the middle of the chain, and then some convert this shorter chain, cellodextrins, cellobios, into even shorter, up to down to the monomers, this glucose. So there are the action is not very simple, so there are different steps. Now, well, here let me see how many slides there are. Well, there are not that many, so let's finish this section. So this previous one was hydrolysis of cellulose. So this stuff made out of only one single glucose monomer, and that can be done easily with the help of acidic catalysts or enzymatic catalysts, like I mentioned earlier. Then if you want to break the hemicellulose, I already mentioned that that's the easy thing to do. So often it can be removed first. So acid hydrolysis of hemicellulose, so it happens in milder conditions. So you can do that. It makes sense that you apply first milder conditions and remove some component. You are left out with lignin and cellulose, which you can then process further. So here it's mentioned that it can be also done only with hot water, and hot meaning 200 degrees or something. So then you need to have a pressurized vessel, of course, or increased pressure to get the water at liquid state. But in any case, so no acid needed. It works just with water. And remember that this hemicellulose, it was made out of several different sugars. So it breaks into the mixture of different sugars as well. Some of the hemicellulose sugars can be utilized for the same process for making of ethanol, and this xylose, this so-called 5-carbon sugars, are more difficult to ferment because natural yeast or enzymes do not easily ferment these xylose 5-ring sugars, but there are genetically modified enzymes or yeast that can do that. But just a reminder. And once, if the acid hydrolysis goes too far, so you end up with levulinic acid. I think this was mentioned already earlier. So this is an example of that unwanted side product. On the other hand, levulinic acids can be converted into esters or to some other chemical, methyl tetrahydrofurane, and these both can be used as a gasoline additive. So in one hand, this, if it goes too far, so this might be possible to still utilize. Here you'll see the methyl tetrahydrofuran. This is just hydroxymethyl. Sorry, no, now I'm mixing things. So the glucose can go further to levulinic acid. Here are the reaction steps. Just to get an idea of the chemical structure. Also, what I didn't mention, that this reaction described here, so there are side products. Solid humics or tars are also formed. So, but there's plenty of more info about this. This is, I mentioned last week something about platform chemicals. So some of these, like levulinic acid and this hydroxymethyl furfural, are considered as these important bio-based platform chemicals that can be converted into various useful chemicals. Then last method, so we covered like acid hydrolysis and enzyme hydrolysis and so on. There is also possibility that you process this biomass with hydrolysis and hydrogenation. So you combine two different methods in the same reactor vessel, and you can also get useful products that way. So you make the hydrolysis, but you add hydrogen into the mixture, hydrogen gas, and also hydrogenation catalyst. So this we went through last time. So there is the carbon is the support, activated carbon, and ruthenium metal deposited on the carbon. That's a typical hydrogenation catalyst. So together with phosphoric acid, so this can convert wood into different sugars, xylitol, sorbitol, and so on. And these, of course, can be then processed further. Okay, I have been now talking quite a lot. Maybe you are a little bit exhausted and confused perhaps. But if you are interested in digging deeper this lignocellulosic pre-treatment methods, so literature has a lot of information about this. So if you want to learn more, so it's certainly possible. So I was only touching the topic a bit. But on this course, the purpose is not maybe to go very deep into these things, but just to get an idea that there are different pre-treatment methods, and it gives possibilities to utilize the lignocellulosic biomass. It makes the utilization easier and improves conversion rates to desired products. And typically it has been done with acid catalyzed hydrolysis and with enzymatic hydrolysis. So these are quite typical steps. Well, the last what I mentioned here, this combined hydrolysis and hydrogenation, these are very rather new developments compared to those two before mentioned approaches. So now we have covered this ethanol production up to the point when we have sugars and we can start to ferment the sugars. So I think we'll have a 15-minute break and then we'll continue with this second part. So, time to continue. So now I go briefly through sugar conversion to ethanol. So there are different approaches to do that. And first of all, this our textbook is presenting several possibilities how to convert these sugars into fuels. And by fuels, I mean, and we understand that those can be fuels as such, or those can be like more typically components that are added or are part of the fuels, as fuels tend to be quite complicated multi-component mixtures. So some of these processes produce one or few of these components that can be used in the fuels. Ethanol we take a look at in more detail today, but I collected this slide because I wanted to highlight that the textbook is dealing with sugar conversion, and not only sugar conversion to ethanol, but there is upgrading of sugars using these zeolite type materials into hydrocarbons that can be used or that are fuel components. There is also so-called aqueous phase processing of sugars, so there it involves catalysts and so on. This we take a look at perhaps later, but also there is it starts from sugars, the same as making of ethanol, but we end up with hydrogen and some hydrocarbons that can be also. These, of course, don't need to be used for fuel production, but these would be suitable, at least the alkanes. Fuel contains alkanes, so why not? The sugars can be also reformed or treated under supercritical conditions, and you end up with, for example, this is explained also in the course textbook. So depending on the temperature, the conditions, so you end up, you can tune the mixture of products, but you might end up with carbon monoxide, dioxide, and perhaps hydrogen. Also, you can ferment, or sorry, you can digest the sugars so that microbes are breaking the sugars into hydrogen and methane, and these also are components that can be utilized as fuels or as components in the fuel production and so on. And these 4 methods or techniques that have been described in the course textbook published in 2006, nearly 20 years ago. So I just put here that these, at the time of writing this textbook, so these were more or less on the research level. So several other methods have emerged, and also some of these have been studied in much more detail. So if you are interested, so there's a lot of literature about these upgrading methods, as these topics have been quite popular. But now we take a look at the ethanol side. The material again so comes 90% from that course book, the article. This link didn't work, so it was a video about ethanol production, but I forgot to remove it. The video doesn't exist anymore in the YouTube. So there are different ways to make the ethanol. There were several different ways how to convert sugars into fuel components. You can also convert sugars into many other chemicals that are more valuable, not as fuels, but something else. But the typical way to do the ethanol is the traditional beer and wine making process. These are those first generation biofuels that we have discussed the generations very often. So this is raw material sugars that could be used as human nutrition. So it's questionable if these are is it ethical and sustainable to convert edible sugars into fuels and so on. And we know that these are not preferred. We prefer beer and wine instead of fuels made out of carbohydrates. Ethanol can be also made in some industries from ethylene. So this is the ethylene is more commonly used for making of polymers, for polyethylene, the plastic that's, for example, you'll find in plastic bags or some liquid canisters, bottles and such. So that's the major use of ethylene. But if you have a facility that produces ethylene and there is not any polymer processing unit nearby, also in some cases, or it makes sense to convert this ethylene gas into ethanol. And there are catalysts and processes to make that. But just that the ethanol, this would be classical fossil-based route for ethanol. But nevertheless, what I have been trying to also point out during the course is that the same organic molecules and material can be made from different raw materials and through different processes. The question is then usually that which raw material is available, which process is available, and then also at that particular time and place, so which maybe is the cheapest alternative. There is nothing special in this slide. I think we have gone through this already earlier, but ethanol is used or can be used directly as a fuel if you modify the engine. And we already mentioned that Brazil is among the largest ethanol producers in the world, together with United States. And in Europe, for example, ethanol is added as the bioethanol is added as the bio component, the renewable component in gasoline, in 95 and 98 octane gasoline. Overall, the sugars are fermented, and so-called Saccharomyces cerevisiae is the regular yeast that we use for for baking, and that converts this glucose sugars into ethanol. So the sugar, this is the molecular formula of sugar. It converts into 2 ethanol molecules and 2 carbon dioxides. Sorry, I will take a glass of water, just a second. So, typically, ethanol is converted with the help of baker's yeast. The Latin name is the Saccharomyces cerevisiae, and very often it's written S. cerevisiae because, well, I will not go into details of this, but the name is that. And the reaction, when you convert sugar into ethanol, so it produces also carbon dioxide. And that's the reaction, you cannot avoid it. But I don't know if it's interesting thing, but related to this is that in some of these factories where the ethanol is produced, so the carbon dioxide is actually also a valuable raw material. It's captured in these production units, and this can be used in the beverage industry or elsewhere where you need a good quality carbon dioxide. So in this case, it's not a bad, or it's also a product that has a value. Also, this carbon dioxide can be sold to greenhouse gases, and in commercial greenhouse gases, so the CO2 levels are adjusted and controlled, because usually the higher up to certain limits, so the higher the CO2 level, the faster the plants grow and produce products like fruits and such. So it has use, it's not wasted. And but the ethanol is the fuel component that can be used, and there are a few possibilities how it's made. Some facts about the production reaction itself. So roughly 50% of that sugar mass is released in carbon dioxide gas, but on the other hand, majority of the energy is bound into the ethanol part and not in the carbon dioxide part. This comes to the fact that this yeast, baker's yeast, it can help to ferment these 6-ring sugars very easily. Here mentioned glucose, mannose, fructose, and galactose. So many of these, the glucose come only, or cellulose is made out of only from glucose. So if you hydrolyze cellulose, you end up with glucose only. If you hydrolyze this lignocellulosic material or hemicellulose, so hemicellulose contains also these other sugars and in addition to this xylose. And this xylose is so-called 5-ring sugar. These are 5 carbon sugar. These others are 6 carbon sugars and the yeast cannot digest or process the pentoses any further. So that is lost material, or it can produce problems when separating the products, so that there is unreacted sugar in the mixture. But what I mentioned, that one can genetically modify these yeast organisms so that they'll also digest and convert pentoses into ethanol. That's kind of modern process development in that sense. It's also a good, I think, to realize that in these fermentation reactions, especially depending if the conditions vary to some extent, so you'll end up making not only ethanol and carbon dioxide, but some other side products can be produced as well. And then it's a matter of question that if these need to be separated, or are the levels so low that they will not influence the use of the ethanol itself. Now we get to the 3 alternatives for ethanol production. The fourth one is this ethylene route from fossil-based ethylene but that's not of interest during this course. The raw materials are totally, or not totally, but are different. So the fully sugar-based possibility based on sucrose. So this was the first generation process. Then if we use water-soluble and digestible polymers, biomass, that is the starch. We also, humans and animals, tend to digest starch molecules. So these are found in potato, corn, wheat, barley, but chemically this is already a polymer. This sugar, sucrose, these are already the monomers that exist in these. So starch needs to be digested. And then the technically more demanding is the second generation cellulosic biomass, so that we have dealt today again. So that's the wood-based material that contains cellulose, hemicellulose, and lignin. And lignin is not sugar. It cannot be fermented into ethanol, but like said, it can be converted into other valuable chemicals. However, it's rather challenging. So these are the different processes, and we'll glance through these now. And if you want more detailed explanations, and you can find it in this graph, and content has been taken from the textbook. So this picture you'll find in there, and it integrates these three different ethanol production processes in the one and the same picture. So now we take a look at this most used, so the sugar-based ethanol, so the sugarcane ethanol process, which is, so I have circled here. And okay. This YouTube video exists, but I was planning to play it during these lectures, but maybe I will not. If you are interested in, you can take a look at it. There is this professor that has done, this is quite old video already, but he makes quite nice chemistry related videos. So the sugarcane process, so this is now showing that lower left corner of that bigger picture. And graphically, so it starts by sugar extraction. So when the sugarcane or sugar containing plants are produced, so the juice is squeezed out, which is rich in the regular sugars. So here no hydrolysis is needed. The sugar juice is directly fermented and processed further, like, or you'll get the ethanol solution, but well, it should be also distilled in order to make the fuels. And sugarcane juice contains roughly 30% of that sugar and some insoluble lignocellulose. So this sugarcane juice doesn't require extensive pre-treatment because there are already these free sugar monomers that the yeast can digest easily. These are some conditions and details regarding this particular process taken from the, like I said, the course textbook. So sugars are first heated. The purpose, like this is yeast or biochemical process. So often this kind of other microbes that come or exist naturally on biomass or come from nature, so those might cause problems, so-called contamination. So once you heat it up, heat the mixture, so you kill the additional microbes, and the idea is that there is no competition between different microbes and the yeast can happily work and produce the ethanol. Some nutrients can be added. So these nutrients are for the yeast, so for the yeast to multiply and also for its metabolism, so that it feels live and well to produce the ethanol. Here are the conditions for the actual fermentation. So about 28% sugar solution, pH slightly acidic, and this is noteworthy perhaps that the temperatures now, these are biochemical processes, and these tend to take place at rather low temperatures and typically close to our body temperatures, and so majority of the microbes and enzymes work at the same temperature as the living organisms like animals and so on. The reaction time, or the time that the sugars are processed, is somewhere between 1 to 4 days. I don't know, like these are just to give you an idea. I think the important thing here is to have an idea that the sugar solution is rather concentrated, 28%. The temperature is rather low, and the reaction times are in the order of days, not in the order of minutes or seconds, like for example in pyrolysis or some other techniques that happen very fast. Once the distillation is finished, so it's distilled, and we are not going to cover the theory of distillation very much, or basically not at all on this course. So it's a simple chemical separation procedure. So the components are separated based on their boiling point differences. It's very much used in the oil refinery, where there are hydrocarbons that boil at different temperature. So to put it, if it's not familiar to you, so if you adjust the temperature to that boiling point, so basically the lower boiling point component can be removed from the mixture. But this is oversimplification. It doesn't work exactly like this. But basically what happens is that this after fermentation, so there is quite a lot of water, and there is like maybe 10 to 15 volume% of ethanol in the mixture. And if you start to heat it up, so the ethanol starts to boil first, and it exits the vessel, and basically it can be separated so that it's more concentrated. But the azeotropic level is some theoretical maximum that if you, not going deeper into theory, but if you have these mixtures of two different chemicals, so sometimes they form so-called azeotropic mixture. So regardless of how well and carefully you do the distillation, so the concentration of ethanol cannot rise above 95% in that exiting gas mixture. This is so that the gas remains this constant composition, and this 95 volume% of ethanol is not yet suitable to be used as a fuel, but it needs to be, this extra 5% of water should be more or less removed before it works better. And I mentioned in the introduction that this distillation could be done by adding their benzene, which is highly carcinogenic and toxic and so on. And that would help to break the azeotropic mixture, and it would allow you to distill it higher than to 95% pure ethanol. But the more, let's say, less toxic alternative is to use these so-called molecular sieves. We talked about this in the connection of catalytic materials. So one can, there are zeolitic materials that have the pore size just small enough to fit the water molecules inside the tiny channels, but the ethanol molecules are larger, they cannot fit into the pores. So when you put these molecular sieves in this azeotropic ethanol water mixture. So the water goes inside the solid material and ethanol remains outside. Once you filter this solid out, so you have purified the ethanol so that the concentration can be very close to 100%. So this is called more generally drying of solvents, very typical approach in organic chemistry. But this is now the whole sugarcane process picture again. So squeezing out the juice, regular fermentation and recovery. So that's removal of ethanol, and what else remains? This vinasse, and that can be used, for example, as a fertilizer, because there are other nutrients and chemicals also in the starting material. So not all is converted into ethanol. Then there is the dry milling process. It's maybe not, let's take this. So it's the right hand side picture here in the middle, or on the right side of picture, more or less in the middle. It covers roughly this part displayed here. So here the starting material is not this water-soluble sugar molecules, but these are the starch-containing food material, like corn grains or potatoes and such. And the first step is to grind it, mill it into small grains or powder, and mechanically process it into smaller. And then this is the same as making also, well, like whiskey and such. So you break the grains by heating them with enzymes, so that the idea of this step is to break with the enzymes this sugar starch polymers into monomeric units. There are different conditions applied. So the same here, like in that previous one, that to remove these microbes, so by heat treatment and so on. And after this pre-treatment or sugar or this hydrolysis step is carried out, so then the released sugars are fermented and distilled, like in the very same way. The same yeast can be used, and this is, you'll get ethanol water solution that contains some 12-14 weight% of ethanol, and if you want to concentrate it, so it's done in a similar way as in all these other ethanol processes. So you distill it, and at some point you remove the leftover water with molecular sieves, or maybe in some cases try to break the azeotropic mixture. Here you'll see that you get this different products, side products, in addition to ethanol in that dry milling process. So this acronym DDGS, distillers dried grains with solubles, and DDG is distillers dried grains. So this is material that can be recovered, and it's quite nutritious material because we started with corn-based or grain-based material. So corn and grain, it contains these fats and lipids and also proteins and some nutrient fibers which are not converted or destroyed in that process. So this can be used. So it's useful, but for us it's more or less like a side product. So this was the second possibility to make ethanol. And notice now we have the big picture here. So in the center there is always more or less the same, like fermentation, product recovery, and and hydrolysis in some of these parts, but the other routes vary slightly. So this wet milling is on the upper left corner, and then it continues in the middle of this big picture as highlighted here. And wet milling process utilizes so-called seeping, milling, and separation steps to process the biomass first. Seeping, I put here what it means. So it's basically soaking the starting material in water, and that's the first part of this. You can also get some useful products out from this, so like gluten meal, feed, corn germ, and so on, which can be used for human or animal food. But this is not useful. This has nutritional value, but it has no value in the in the fermentation. So therefore, it's separated there, and you are left out with ethanol solution that will be processed in a very similar way as that previous one. I don't know if this is making, hopefully it makes sense to you. However, these different steps, conditions, and processing is explained in so you can read it in the course textbook. And the last possibility to process this is the fourth alternative, the lignocellulosic route, and it's here. I have tried to illustrate it in the big picture. So there is the cellulosic biomass that goes through the pre-treatment to make it more accessible to hydrolysis conditions. Once after hydrolysis, the formed sugars are fermented, and then the ethanol is separated, distilled, and that's the process. So the woody biomass is first ground into small granules or powders or chips, and then it's acid hydrolyzed with, this is probably the pre-treatment step. So sulfuric acid pre-treatment to get rid of the or release the hemicellulose sugars and the acetic acid. Second part is neutralizing. It's mainly neutralizing. Of course, you have the main acid source is the sulfuric acid used for this particular step. But from that hemicellulose, when it breaks, so it releases also some amount of acetic acid. So in that next step here, it's neutralized by adding some basic material, lime. And this neutralizes the acid. You'll end up with material that is then hydrolyzed. So this actually was the pre-treatment step where the woody lignocellulosic material is made more accessible to the actual hydrolysis step. And once the hydrolysis takes place, so then it results into regular sugars that can be fermented. This is something that I have mentioned already many times, but in this case, when there is these 5 carbon sugars, so one, if you don't want to separate these and use them elsewhere, so you can ferment these xylose sugars with this help of modified microorganisms, but these are not naturally occurring. So the baker's yeast would not do the job fully. It would only convert the 6-ring sugars in this case. So now we covered 4 different processes, how to make ethanol from different starting materials. So there are I go back a little. So basically, if you take a look at this bigger picture here, so although its ethanol production is rather simple technically, there are not that many steps, but on the other hand, it becomes already quite complicated process because there is often this minimum except in that cane juice process. So you end up doing hydrolysis, fermentation, product recovery, and distillation. So there are already quite many steps. And in some of these you add their pre-treatment steps in between, which might not be only one, but there can be 2 or 3 steps in reality. So basically simple process, but when you do it in an industrial process, so it becomes already more complicated. Also, each arrow here, it's a kind of a separation step. So you separate something out from the other. So that's also adds to the complexity of that process. But these are not technically or by any means super complicated or multi-step processes, but yet it becomes a bit more complicated. This picture is, we don't need to understand anything else from there except that I think the idea here is that if you treat the real biomass, the lignocellulosic biomass, and thinking about ethanol, so you more or less eventually end up with these 6 carbon sugars, the glucoses, which are easy to ferment with even natural baker's yeast that you can find in the nearby shop. However, the hemicellulose result into formation of these 5-ring sugars, and those are the more challenging component here. So like mentioned, so you need special microbes to ferment those 5-ring sugars, 5-carbon sugars, sorry. I tend to mix this. They have 5 carbons in the sugar structure. Or alternatively, those have to be separated, or they will not react in the fermentation step and remain as an unused fraction of that material. Few more slides regarding the ethanol process. So something about the cost. So production understandably will depend a lot on the cost of producing the biomass and different steps of that process. It was mentioned in the previous slide set that the pre-treatment step might be in lignocellulosic material the most expensive one. Here are some numbers so that the feedstock, the actual biomass cost can be like half or 1/3 of the ethanol production cost, depending on the starting material. This table summarizes some of the production costs in more detail. Of course, this is an older material, but one gets an idea of the order of magnitude and such from these figures. So there is numbers for sugarcane, corn grain, corn stover, and as a reference also diesel fuel. But the data and the numbers are not, this is like 25-year-old data. So if I had to make a guess, so currently the numbers are, let's say, better in terms of energy efficiency and many other improvements. But if the feedstock costs are half or 1/3, so these are something that you cannot influence or improve much by process development, process optimization. So if the wood costs what it costs, so you have to pay and one can collect some kind of idea that the production cost is highest with that sugarcane, so food-based sugars, and then the lowest one is with these second generation lignocellulosic sugars. The corn grain is there in between. Fossil energy ratio is listed here. So it's these numbers, so it's the fossil energy needed for ethanol production divided by the energy content in the ethanol. Very long sentence and complicatedly said, but if this number becomes 1, so you use as much as fossil energy as the product contains, and that means that it doesn't make any sense to produce fuel that the production consumes the same amount of fossil energy. But these numbers are telling that the overall, if you look at the lowermost numbers here, so at least ethanol based on sugarcane and based on lignocellulose corn stover, so we'll gain net energy, and it makes sense to produce these. And also for corn grain based, this 0.92 reading is quite high, but I remember that there was a very active debate by the time this article was published, and a bit earlier already, and I mainly took this table here because there were lots of concerns that the bioethanol production is not, there is not really a net energy gain in the production. However, this seems that there is really, and it's useful to make bioethanol, so it's not, there is net energy gain in the product itself. Okay, this is, well, more or less the same, that this energy ratio decreases in when going towards the lignocellulose. Is it in line with the, well, I don't see it directly from this graph table, but also if you produce lignocellulosic biomass, so you always produce or separate lignin, and that's also some fraction that contains energy, and it can be used, like mentioned here, to burn for heating, and the heat is required especially for the distillation. So in ethanol production, so the distillation is inevitable. You need to distill the diluted aqueous solutions of ethanol to concentrate them, and distillation steps are very energy intensive because it requires boiling of that mixture. So you need to heat it up to the boiling point and keep it there so that the distillation proceeds. And of course, in principle, you could use the heat in lignin to do the distillations. And I think it's also used. It's not just my speculation. So in summary, so we covered 4 or at least 3 fundamentally different processes for making ethanol. So this is just a summary. We don't need to spend a lot of time going through this, but there is the sugar-based production, which only in principle needs the fermentation and then the purification steps. Then the other 2 need also pre-treatment and hydrolysis in order to process the sugar polymers into sugar monomers. The rest of the process is similar in all these 3.